Let's recall this Taylor series that I mentioned just briefly. And the idea was that we just keep adding terms. If we have a function that is, say, infinitely differentiable, so we can differentiate sort of forever, we just keep adding terms like this. And this is the Taylor series for f of x centered at x equals a. Now, there should be a lot of questions that come to your mind about this, because this is a sum over infinitely many indices at least. So question one, or maybe I'll just say question, for what x is this a function? And I mentioned this briefly when I first wrote it down, right? Well, if you take and evaluate, you put an x in here, and then you add over these infinitely many terms, how do you know you're getting a number? That would mean the function is, that this is defining a function at x, right? Well, we know one answer. One answer is obvious. At least it will be after I mention it, I hope. Answer number one, certainly no matter what your little f is, provided it's infinitely differentiable so that you can write this down, but certainly at x equals a, I'll write it this way, t infinity f a comma a exists as a number, is defined. Because what happens? If you evaluate these terms at a, and we practiced this a little bit when we first started talking about polynomials and rewriting polynomials at different centers. If you evaluate at a, every single term vanishes because you have a minus a to a power, except at k equals 0. So we do have that when you evaluate this at a, we just get the 0th term, which is f of a. Okay, and this is, well, a finite number. It's just the original function value evaluated at a. Okay, well, we would hope that there are more x values so that this is actually a function. Namely, you can put in an x value here, and then with this infinite sum, you get a number. So answer two, I would say, is how do we even define this? Because as I mentioned, we're just adding infinitely many terms. How can you precisely define what you mean by this? And so this comes in, I guess, answer two. How would we define this? Or maybe this would be question two, how would we define this? But let's take this definition, is that this, well, what's the only thing that makes sense for what this could be? It's a limit, okay? It's a limit as n goes to infinity of, well, maybe I'll write it twice, two different ways. First, I'll write it like this, Tn f x a. So you take this nth order Taylor polynomial here. This is, as we know, this is the partial sum, for example. You just cut it off at degree n, and then you take a limit as n goes to infinity. Or if you wanted to write this, a limit as n goes to infinity, this is what I was starting to write, x minus a plus, and then this goes out to the nth derivative at a over n factorial x minus a to the n. Maybe I'll put square brackets. Okay? So this is the way that we would define this accurately, instead of just this idea of thinking about adding infinitely many terms. And so the question becomes, when does this limit exist, right? If this limit exists, then this Taylor series defines a function, and maybe I'll put that as part of the answer. If this limit exists, for some x value, then this exists. Or I will say then this exists at x. And what I mean by this is if this limit exists as a finite number for some specific x, then this thing will be a function at x, or little x will be in the domain of this. Now, finding, for example, if you take a general power series, which I mentioned this briefly, all that means is instead of these being the specific coefficients, we just put some general coefficient ck, say here. If you take a general power series, the set for which the power series defines a function, or one way to say that is converges, this we will get to later. We have to go talk about series of numbers first. So in particular, part of this question we will not fully answer today, and I'm going to ask a related question, which I will only sort of touch on the idea today because it's quite deep theoretically, and it's good to know the idea. I will say you would see more examples or further depth in the theory in a more advanced math class. Question number 2, and this is a separate question, although this is the one that I will touch on more today, is for which x does this, oh, well, okay, I'll write it like this. I could have just written this as t infinity, but it's fine. So this is the Taylor series for which x does this equal the function. For which x, maybe I will include some words above, does the Taylor series for f of x equal f of x. And of course, in this question up here, I am leaving off the center, but you see the center here. Now this is actually a different question, and you won't have the same answer all the time because this is different. The first one was just, does this equal something? Does this, well, the word we will get to is converge. Okay. But this can converge and not necessarily equal this, but this is the question I'm more going to address today. So this says, if you add up these infinitely many terms, when does it actually equal the function? And this is what you would hope, and we will see this equals many times. You would hope this to be the case because what have we discussed already? If you cut this off and take the partial sum, right? So what do we know? Oh. We know for x near a that if you add up just to n, you take the partial sum up to n of this. This is approximately f of x. So this is a good approximation. We've seen pictures. We started last time calculating error as to how good is this approximation, right? So then, well, it's very natural to think if you just keep adding them up forever that you will actually equal the function. No longer is this an approximation if you just keep adding forever. The question is, would we get actual equality? So let's discuss this a little bit right now. Okay, what's the idea here? Well, it goes back to the discussion we had last time, which involved the remainder. So what do we know we recall the remainder. This was the function minus the Taylor polynomial. And we also, for example, could write the function as the Taylor polynomial plus the remainder, right? Well, now let's just think about, I've already defined what this Taylor series is. We take this, we take a limit as n goes to infinity, right? So let's think about this for a moment. I'm going to take a limit as n goes to infinity on both sides, okay? Limit as n goes to infinity here. This would be, well, there is no, okay, I'll just write it. I was going to say there's no n here, which there's not. It's just a function, but I will keep this here. It's fine. Okay. Now, what do you see? Well, hopefully you see here, watch, as this goes to infinity on this side, if this is equal, right? Then as you take this limit as n goes to infinity, this Taylor polynomial converges to the actual function right here. And then this side is 0. And so this would say that the remainder goes to 0 as n goes to infinity, right? But then also, if you think about it over here, if you have a remainder going to 0, that's thinking about this side, if the remainder goes to 0, then, well, over here it says that this limit is 0, and this is, there's no n, it's just constant with respect to n, so that would say that the limit as n goes to infinity of this nth order Taylor polynomial equals the function. So what we see here is this. We see, I will write it here, the Taylor series at A equals the function. This is this infinite sum, okay? We see this is true if and only if the limit as n goes to infinity of the remainder equals 0. Okay, so this is a condition that is required and equivalent to the Taylor series centered at A to equal the function. And this is just for some x. Okay, so if for some x these two are equal, then the remainder will go to 0. And the other way, if the remainder goes to 0, then these two are equal. Okay, well, what can we use this for? Well, maybe I will only do a few examples. I'll do one main example and then I'll speak about a few others. So it is the case that for many functions that we know, that we have seen, that the Taylor series converges for all x to the actual function. Okay, for example, sine, cosine, e to the x. These are very nice because their Maclaurin series converge for all x and equal the function for all x. I think I mentioned that with e to the x. But it's not the case that this happens for every single Taylor series, without a doubt, or even every single Maclaurin series. So we will see today, and our very first example, where I point out that it doesn't converge for all x, and it doesn't equal the actual function for all x, okay? But first, let us look at one that does. Let's look at f of x's sine of x, and let's look at the Maclaurin series. Now, we did the Maclaurin polynomial, I think maybe 5th order. This was one of our first examples, but let's go ahead and write out the series. Okay, and I'm going to also look at the remainder, because this is how we will be able to justify that the Maclaurin series equals the sine for all x, is by showing that the remainder goes to 0. Okay, and then we evaluate at 0. This we have done a few times. We did it for the sine, we did it for the cosine, but I will do it again for completeness. Okay, I think this is the blue that doesn't have as much juice. I will leave it on the floor. Okay, this one's better. Okay, I will just do enough to see a pattern, and I will not simplify the numbers because it will help me in getting the pattern for the series if I don't simplify as I'm calculating. Okay, well, we just start taking derivatives. And then we have positive sine. And we're back at cosine. Okay, this will keep going, right? We have discussed this, both working with the sine and working with the cosine. Now we evaluate at 0. Okay, in fact, this is the exact calculation I did to get the 5th order Maclaurin polynomial, but I will write the general series now. Okay, then we divide by k factorial. Well, I will leave this because it's going to help me. And you could imagine I will do a few more because, as I mentioned, I am actually looking for the pattern. So if I did, say, 6 and 7, this would be minus sine. This would be minus cosine. We'd have 0 minus 1, 0 negative 1 over 7 factorial. Okay? Now, we will be able to write out this in summation notation. So we have, it's going to be, so t infinity f x 0 equals, it's going to be x over 1 factorial minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. Okay, then this keeps going. Okay, let's write it in summation notation. But you see, it's not going to be indexed the same because here, well, the way I have it indexed here, which came from the derivatives, the even terms are all 0, and we don't see even powers here. Now, if we step back for a moment and think about the sine function, it makes sense to only see odd powers because the sine is odd. And when we did the cosine, we only saw even powers, and this makes sense because the cosine is an even function. Okay, so it's sort of connecting your knowledge of trigonometry to looking at this Maclaurin series. In any case, we are going to have to index differently to write this in summation notation. So let's think about doing that above. Here, well, this will now be my k equals 0 term in my sum. This will be k equals 1 in my sum, k equals 2 in my sum, k equals 3 in my sum, like this, because I can't add and have these be the first 7 and say, well, it's just 0 when it's even, something like this. That's not how we look at power series. So this would be a new indexing that will help me write this as a sum. Okay, so let's do this now. This is a sum, k equals 0 to infinity. If you notice, we can compare k equals 1, 3, k equals 0, 1, k equals 2, 5, k equals 3, 7. The coefficient we see here is x to the 2k plus 1, right? Now you can check if you don't believe me. When k equals 0, we get 0. When k equals 1, we get 3. Like this. k equals 3, for example, we get 6 plus 1, 7. So this works. Then the factorial we see matches. And then we're not finished because these alternate in sign. We have a -1 to something. And you see negative k equals 1, positive k equals 2, negative k equals 3. There will be a -1 to the k. Okay, so this is a way to write out the Maclaurin series for the sine in summation notation. Now, let's fix x. So x can be any real number, but it's fixed, okay? And then we will show that the remainder here goes to 0 as n goes to infinity. What this says is that the sine of x equals this. This is the Maclaurin series we just calculated. Okay, so the sine literally equals this for every single x. Okay, this infinite sum. And let's do this now, okay? So x is fixed. Okay, very nice. How are we going to show the remainder goes to 0 for this x? Well, let's think about absolute value of the remainder. This equals, well, this is the error, right? It's fine. But this equals, by Taylor-Lagrange, absolute value. This would be the n plus first derivative at some c over n plus 1 factorial times x to the n plus 1. Okay, and I should say for some c between 0 and x. 0 is my center. This fixed, well, it's fixed but arbitrary, but this fixed x is where I am computing my error for, right? The way I have it written, maybe x is negative, then 0's here, or maybe 0 and then x, and it's fine. The wording works for either one. Okay, well, what do we know about the n plus first derivative? I'll write it over here, and then I will erase it. We've seen this, well, over here with my chart, but also in some other videos. The n plus first derivative is one of these four. It's either plus or minus sine or plus or minus cosine, okay? Now, all of these in absolute value are less than or equal to 1 for every single x or for every single c, no matter x, right? X can be any real number, positive, negative, does not matter. And then c is some number between 0 and x, fine. But in absolute value, these are all less than or equal to 1. So I may replace this part here with a less than or equal to 1. And that's what I will do now. Let me erase this comment. So this error, absolute value of the remainder, is less than or equal to, well, it's absolute value of x to the n plus 1 over n plus 1 factorial. Now, I'm going to make a comment, and then we'll look at some pictures in a moment. Here's my comment. Let me just write this in terms of n. Here's n plus 1. It's fine. Okay. My comment is for any x. Okay, again, x is fixed. If we take a limit as n goes to infinity, I'm going to write it like this because it matches, but here this would hold 2. This goes to 0. Now, why would this be the case? So let's think about it for a moment, and then I will look at a few pictures. Okay, why would this be the case? Well, if you think about this, in the numerator and in the denominator, I have the same number of terms. Okay, so notice here that absolute value of x to the n over n factorial equals its absolute value of x, absolute value of x, absolute value of x. Okay, absolute value of x. There's n of them there. And then I have n times n minus 1 times n minus 2 down to, well, this is going to be 3 times 2 times 1. Okay? So at some point, there's going to be, you see, the denominator, these are growing, and these are just fixed. Absolute value of x may be huge. Maybe it's 1,000, and, absolute value of x might be 1,000. And certainly if n is 2, this is going to be big, or n is 3, or something like this. But eventually, this n in the denominator is going to be bigger than absolute value of x. So eventually, things of this form will be less than 1. And you keep multiplying. So at some point I'll have, let's take the 1,000 case. I'll have 1,000 over 1,001. Then I'll have 1,000 over 1,002, 1,000 over 1,003, 1,000 over 1,004. I'm going to get more and more and more numbers less than 1 multiplied by, well, this part is still just now some fixed number. As n gets large and larger, this will go to 0 because this is a fixed x. Okay. So what I'd like to look at is this graph of absolute value x to the n over n factorial. And what I claimed just moments ago was that for any x, so fixed x, that as n goes to infinity, absolute value of x to the n over n factorial, the limit is 0. Okay? So here, well, I had to use different letters just because of the way Desmos likes its input. But this here at the top, this m equals, this is my fixed x. And I have it set to range between minus 60 and 60. Although by changing my window, I could really look at any x. So this is x, okay? And then you see this function, this here, this d of t as I have it written, but this is absolute value of x to the n over n factorial. And then these points here, if I take off the graph, the points are just plotting it at integer points n. 1, 2, 3, 4, like this, because this is what we are really looking at. If you look at absolute value of x to the n over n factorial, it's just ranging over n, say, non-negative integers. Well, okay, so let's look at a few. And I have these only going up to n equals 300. Of course, for this would be x small. There's x equals 3. I don't even see this increasing that much, but you have to look at my scale. This first line here is 2 times 10 to the 6th, which is very large. Okay, so here x is 3, but even for large x equals 40. Okay, this is going to be big. As you see, if I graph the function, you see it is increasing for n at first. But then, and this is what I was commenting on, there is some point where it starts decreasing. And you see, in fact, that even this is a pretty big n, or x, I should say, that this x to the n and absolute value over n factorial eventually goes to 0. And if I use these negative x's, it looks the same because here in my function, I'm looking at absolute value. But it is the case. If I went outside this window of 60 and I stopped at 60 just because I'm only going up to 300, and you can see that this x to the n over n factorial, even for x equals 60, you can see in my window n going up to 300, it goes to 0. If I picked an x bigger than 60 or less than minus 60, well, I would just have to increase this, how far I go out, to see that, in fact, this goes to 0, but it holds for all x. If you fix x, that's what this slider is doing. Fix x, then absolute value x to the n divided by n factorial as n grows without bound. That's this axis. This is the n axis if you see the way I have it plotted. This limit is 0. So now my comment is here. We have in absolute value, we are less than or equal to something that's going to 0. Well, you might have heard the pinching theorem or the squeeze theorem like this from Calc 1. This is going to 0. This is, well, it's like this. Okay, I'll actually write it. So then we have this, the remainder is less than or equal to and it's bigger than or equal to negative of that. Okay, this going to 0 as n grows without bound. This, well, it's negative of this, also going to 0 as n grows without bound. Okay, and this is stuck between the two. If you're stuck between two things that are both going to the same number, then it forces this too. This is the squeeze theorem or the pinching theorem, depending on the language that you learned. It says the same thing. Okay, so maybe I will make this comment over here. So then as this goes to 0, comma, we see that the remainder goes to 0. Okay, so this argument justifies why this Taylor, or Maclaurin, I should say, series for the sine actually physically equals the sine for all x. Okay? We can also show by looking at remainders that the cosine of x equals, and now we've seen this a little bit, but this is an x to the 2k over 2k factorial with a minus 1 to the k, that this equals this for all x. And we can also show, for example, e to the x, which I mentioned that this is a sum, k equals 0 to infinity. This is x to the k over k factorial for all x. So these are very nice Maclaurin series because the functions equal the Maclaurin series for all x. Okay, but not every function equals its Taylor or Maclaurin series for all x, and similarly not all power series converge for all x. So what's an example? And this is actually a pretty important one. It will come up even more so in the next video. What's an example of a function such that the Maclaurin or Taylor series does not converge for all x? Well, let's look at this function. F of x is 1 over 1 minus x, and we will find the Maclaurin series, and then we will see that this in fact does not converge for all x. Okay, well, let's do this below here. This is quite a fun Maclaurin series to calculate, as you'll see with the coefficients. Here we go. We need to do enough to get a pattern of x. The kth derivative at 0, then the kth derivative at 0 over k factorial. Because I'm looking for a pattern, I'm not going to be simplifying the fractions that come up. Leaving them unsimplified help you find a pattern, in my opinion. Okay, so let's do, well, hopefully we can see the pattern with 3. I'm going to rewrite the function like this because that will help me when I take derivatives. Well, what happens when I take the derivative? I would bring down the power, 1 minus x, to the minus 2. But this is not the derivative. You need to multiply by the derivative of the inside function. This inside function has derivative -1. So this turns this here. Okay? So far, so good. Now we differentiate again. Well, it would be -2, 1 minus x to the minus 3. But again, multiply by the derivative of the inside function. Okay, now, one more. We were going to get, maybe I will go ahead and write it, to the minus 4. Now we just need to evaluate at 0, and this is the easy part because 1 minus 0 is 1. So here we get 1, 1, 2, and 3 times 2. If we think, and I'm running out of space, but if you think about the next one, we would have a 4 times 3 times 2, right? Because it would be minus 4 times 3 times 2 times -1. And similarly, what we're seeing here is we're getting the factorials. Okay, now divide by k factorial, and you see it's 1, 1, 1, 1, and this would continue. The next term, we would get 4 factorial over 4 factorial, 1, like this. Okay, well, this Taylor series, or centered at 0, or equivalently Maclaurin series, is a sum k equals 0 to infinity of x to the k, or you can write it like this. It's 1 plus x squared plus x cubed, like this, okay? So this is just, the coefficients here are all 1. I have erased to give us more space. I rewrote the function f of x is 1 over 1 minus x. Then we computed this. This is the Maclaurin series at 0. And this has a special name. It's called geometric series. I will just say we are going to spend a lot more time with geometric series when we get to series of numbers, okay? But for now, I just mentioned that name, and I will in fact do a lot more with this when we get to series of numbers. Okay, but what can we do today, or what will I say about this today, is I'm going to make the observation, because we saw the sine, cosine, e to the x, those functions, the Maclaurin series actually equals the function for every single x value, which means two things. It means that the Maclaurin series actually, when you add it up, you actually get a finite number for every single x, and that it agrees with the function. But here, this is definitely not the case for all x. So here, the Maclaurin series here cannot, or I will say is not, a function, I'll say it this way, is not a function for every x. It cannot be a function here, okay? Now, and in particular, it's not equal to the original f of x for every x. It cannot be. Now, let me show you two examples. We will see, and then I'll mention precisely when the Maclaurin series equals this. I will mention it, which we will see more later, as I mentioned. Okay, well, let's take, for example, x equals 1. What happens when we add, or let me use this notation. How do we get a handle on this? Well, the definition, we take a limit as n goes to infinity of the nth order Maclaurin polynomial evaluated at 1. So we take t n f 1 0, which is the sum k equals 0 to n of 1 to the k, and then we take a limit as n goes to infinity. Here we would have a limit as n goes to infinity. And this, by definition, is what this here even means, or what this here even means, right? If this limit exists as a finite number, then this is something at 1, okay? If the limit doesn't exist as a finite number, then this is not a function. We don't have a value to assign 1, like this. Well, what happens here? Look, 1 to the k is just 1. So we are adding up 1 in times. This is 1 plus 1 plus 1 plus 1. Well, no, we go 0 to n. There's going to be n plus 1 terms. 1 to the 0 is 1. Then we have 2. There's n plus 1 terms. Okay, so this is n plus 1. This is infinity. So you see that this 1, 0 is not defined as a finite number. So it's not a function at x equals 1. Okay, now you might be thinking, well, that's not a very good example because 1 is not even in the domain, and it's not, right? 1 is not in the domain of my original function. But let's pick something in the domain, and we will have the same kind of thing. Okay, so what is in the domain? X is minus 1 is in the domain. Now, let's look at my function. What is f of negative 1? It's 1 over 1 plus 1. This is 1/2. Okay, so if this were an example like e to the x sine and cosine, this infinite sum where we take the sum minus 1 to the k, right? That's what this is. Well, this would be equal to 1/2. That would say that this equals this at x equals 1/2. At x equals minus 1, excuse me. But let's see that, in fact, it's not the case. So let us look here. We would take a limit as n goes to infinity of t n f minus 1. This is a limit as n goes to infinity of the sum k equals 0 to n minus 1 to the k. Now let's write this out of, well, let's just write out the terms here. It will be easier to see what's happening. Well, when k equals 1, when k equals 0, minus 1 to the 0. When k equals 1, minus 1 to the 1. When k equals 2, positive 1. When k equals 3, negative 1. When k equals 4, positive 1. And this goes out to, let's see, we will have a minus 1 to the n. What is this? Let's think about it. I will write it below. This quantity is either, let's see, it's 1 if n is even. It is 0 if n is odd. This partial sum is either 1 or 0. So we have something 1, 0, 1, 0, 1, 0, 1, 0. What's the limit as n goes to infinity? Does not exist. This limit here does not exist. Okay, well that means this infinite sum does not exist as, it's certainly not a half, but it does not exist as a finite number. So we see here, where can I write? Maybe I will erase my function value. We see here as another observation that t infinity f minus 1 is not defined. Okay, So here's two different things. Of course, minus 1 is in the domain of the function, but still, this power series does not, what's called converge there, okay? It is not defined as a finite number at minus 1. Okay, now I will close with one more comment about this, and we will really see this when we get to series of numbers and I come back to the geometric series. But I will close with a comment today. Comment. We will show the following: that 1 over 1 minus x equals this, provided, or maybe I should say if and only if, because this is definitely the case, if and only if absolute value of x is strictly less than 1. Okay, so this power series equals the function when the absolute value of x is less than 1, even though the function itself is defined everywhere except for 1. So this is a general, like, I guess, caution. It's not the case that every single function equals the corresponding power series as long as you're in the domain of the function. No, it's not the case. Okay, and this function in particular is the first one that we see, at least that I have discussed today, where this happens. So here, this function is corresponding series called the geometric series, and this converges, well, and equals this. This converges, I should say that this actually equals something and equals this when the absolute value of x is less than 1.